This work is on the formula complexity of the iterated permutation matrix multiplication problem. So this problem, denoted PMMNK, is the problem of computing the product of k n by n permutation matrices. Okay, or as a function, let's say we want to compute the 1-1 entry of the product of these matrices. So we can visualize the input as being given by a layered graph of permutations. So each matrix Mi specifies a permutation, or if you will, a matching, which we denote by a bipartite graph. And note that each of the n vertices on the left is connected by a unique path to a vertex on the right. And so the question is whether the top green vertex is connected to the top green vertex on the right. So here we see we have a yes instance, so the unique path indeed connects the top elements. So the 1-1 entry of the product is 1. And a no instance looks something like this. So what is known about the computational complexity of this problem? Okay, as we'll see, this is a very important problem, and for different parameters, it captures different complexity classes. So in the setting where n is just 2, this problem is easily seen to be equivalent to the parity problem on k bits. So there's a path from 1 to 1 going across, if and only if the number of crossings is even. When n is 5, or any constant bigger than 5, then this problem is complete for the complexity class NC1 by Barrington's theorem. And recall that NC1 is equivalent to the class of languages that are decidable by polynomial size Boolean formulas. Okay, we'll be interested in the formula complexity of PMMNK for when both n and k are growing parameters. So in particular, when k equals n, or when k is poly n, then this problem is complete for log space. And in general, it's computable by formulas of size n to the order log k. Okay, so something which is super polynomial when when both k and n are growing. And note that a matching n to the omega log k lower bound for any growing parameters k and n, any super constant k and n, would be separating NC1 from log space. And this is the motivation for this work, for trying to understand the formula complexity of PMMNK and size depth trade-offs as well. So when we speak about size depth trade-offs, we consider Boolean, so AC0 formulas. So that is unbounded Fan and OR gates, and we also have negation gates at the bottom, but only D layers of gates, where D is some either some constant or some function which is sublogarithmic in n. Okay, so the aforementioned formulas of size n to the order log k for this problem, so these are the well-known recursive doubling construction that we'll see in a moment. This can be implemented by AC0 formulas of depth just log k. And for any depth d plus 1, which is at most log k, this problem has formulas of size n to the order d times k to the 1 over d, okay, by another very natural sort of divide and conquer algorithm. As far as lower bounds, so in previous work, we proved tight n to the omega log k lower bounds for this problem, up to depth, which is order log n over poly log n, okay, for some small but super constant range of k, so for k up to log n. And this lower bound, interestingly, even though it's for AC0 formulas, it is not proved by a standard bottom-up depth reduction type argument, and it doesn't produce the standard size depth trade-offs when d is less than log k. So the open question from this, left open by that previous work, was whether we can prove better lower bounds when d is less than log k. Okay, so that's what we address in this work. So what else was known? So in the case where n equals 2, this completely tight trade-off for parity has been known for a long time. So the trade-off for circuits okay, without this factor d in the exponent is, well, this was the classic result of Hastad, proved by the original switching lemma. And the extension to formulas was proved more recently. But as for the general PMM-NK problem, when both K and N are growing, the best lower bound known due to Beam and Pagliazzo and Patasi is of the form n to the omega k to the 1 over something which is exponential in D. So this was proved by a special purpose switching lemma, but it has a very poor dependence on D. More recently, a nearly tight trade-off was proved, not for PMMNK, but for the more general Boolean matrix multiplication problem. Okay, so just you want to compute the product of K n by n Boolean matrices, which are not necessarily permutation matrices. And so this problem has a different nature from PMMNK. So it's complete for NL, non-deterministic log space, whereas PMM is complete for log space. And this size depth trade-off was actually obtained via a reduction from Sipser functions to Boolean matrix multiplication, whereas it's unclear or it's if such a reduction exists to permutation matrices. Okay, so different technique was needed to address this problem. So the results of this work were able to prove a size depth trade-off for PMMNK, again for some super constant, slightly super constant K, of the form n to the d times K to the 1 over 2d. Okay, and this is tight up to the factor 2 that appears in the second exponent. However, in the monotone setting, if we have AC0 formulas, which don't have negation gates, we're able to get the completely tight n to the omega d to the times K to the 1 over d trade-off. Okay, this result is not exactly for iterated permutation matrix multiplication, but instead for the problem with subpermutation matrices, which this is the monotone version of PMM, where we consider matrices that have at most a single 1 in each row and column. The reason is that PMMNK is a slice function, okay, for which it's known that monotone and non-monotone complexity coincide. So in order to say anything stronger in the monotone setting, we need to consider the monotone version of this problem. Okay, so I'd like to review some of the upper bounds that are known for this problem in order to motivate the lower bounds that I'll be discussing. So to start off with, the classic divide and conquer formulas for not just for permutation matrix multiplication, but for the iterated Boolean matrix multiplication. All right, so we're going to get formulas of size n to the log base 2 of k by the classic Sadfich's divide and conquer algorithm. And so the idea is to find all paths from the left to the right. We find all paths from the left to the middle and all paths from the middle to the right, and we merge the resulting subcomputations by performing a single Boolean matrix multiplication. Okay, and if you just unfold this recursion into AC0 formulas, you get something like depth 2 log k and size n to the log k. Now, interestingly, for permutation matrices, you can do slightly better. You can get formulas of size n to the 1/2 log k. And this is based on the observation that if you take a random set of size root n, okay, on both the left and the right, then an expectation is going to be a single path that starts and ends in those two sets of size root n. And using this, yeah, there's a different divide and conquer you can do, which saves a factor 1/2 in the exponent. And this is something which only works so far as we know when you have permutation matrices. Now, these two algorithms, we can describe their behavior in terms of what I call join trees. So these are just a join tree formally. Okay, this is a formula. You can think of it as a formula that computes the path graph of length k. Okay, and it's starting off from individual edges where the only operation is you take the union of subgraphs. Okay, so we can think of this as a formula whose gates are labeled by the union and whose leaves are single-edged subgraphs, and then the root is computing the path of length k. All right, so equivalently, we have a rooted tree whose leaves are labeled by the edges of the path graph, where each edge occurs at least once, okay, but possibly more than once. So here's the recursive doubling join tree, okay, that is sort of describes the behavior of these two algorithms we saw before. So we get a path of length 8. We obtain it as a union of two paths of length 4, and those as unions of paths of length 2 all the way down. Okay, so this has depth log k and corresponds to these and to the 1/2 log k size formulas for PMM and k. Here's a different recursive construction of what I call maximally overlapping join trees. So obtain a path of length k as the union of two paths of length k minus 1, so overlapping paths and all the way down. So this is a join tree with depth k. And somewhat surprisingly, this turns out to correspond to different formulas for PMM and k that also have size n to the 1/2 log k. Um, and yeah, again, this is something which only works for permutation matrix multiplication, not for the more general Boolean matrix multiplication. And sort of in between these two kinds of join trees, we have what another recursive scheme called a Fibonacci overlapping. So if we have a path of length whose length is the ith Fibonacci number, we can obtain it as a union of two paths whose length is the I minus first Fibonacci number all the way down. And interestingly, this turns out to give formulas of depth order log k and size n to the 1/3 log base golden ratio of k, which turns out to be something slightly less than n to the 1/2 log k. And there's some empirical evidence that this might be the optimal constant. Okay, so this is all from previous work, and these upper bounds all have depth at least, so omega log k. And in this work, we're interested in depth which is less than log k. So there's a very natural size depth trade-off, so upper bound, which corresponds to depth D join trees, where we obtain a path of length k as a union of k to the 1 over d consecutive paths of length k to the d minus 1 over d. Okay, so this recursive scheme. This is a generalization of this recursive doubling when your depth is constrained to be d. Right, and this gives the formulas of size n to the d times k to the 1 over d. So those are some upper bounds, and we prove lower bounds in this work, and using what's known as path set framework that was introduced in previous work and further developed in this paper. So the path set framework, you can view it as an elaborate reduction starting from an AC0 formula that computes a PMMNK and reduces it somehow to a join tree computing the path graph of length k. So a much simpler combinatorial object. And this sort of goes through the following steps. I mean, first, actually, we take our AC0 formula and we convert it to a De Morgan formula with Fanon2 and logarithmic depth, but which still has a property that each node in this De Morgan formula is an AC0 function. So in particular has low sensitivity, which lets us use switching lemma and things like that. Those get converted to something that we call path set formulas, some simpler class of formulas, and that gets further reduced to join trees. Okay, and so yeah, this is where the circuit complexity comes in this reduction. I'll be focusing more on the lifting theorem that emerges from this framework. Okay, so really, yeah, the takeaway is that we can this reduction gives us a way to lift lower bounds for some combinatorial parameters of these join trees. We can lift those to lower bounds for AC0 formulas computing PMMNK. As well as unbounded depth monotone formulas. Okay, so the technique actually works in those two settings. And what we do in this work is we refine that method in order to get depth D lifting theorem. Okay, so there's a certain notion of depth D join trees. Well, actually, different ways to measure the depth. It turns out to be quite interesting, but we are able to get lifting theorems for both circuits and for formulas, and actually both for AC0 as well as the SAC0 setting. So SAC0 here means so semi-unbounded fan-in. So you have unbounded fan-in OR gates, but you have AND gates which are restricted to some bounded fan-in, something like n to the 1 over k. So we get lower bounds in all of these different settings. Okay, and just to mention, the reason that this didn't come out of the previous work has to do with this conversion to De Morgan formulas, where we sort of lose the depth of the original formula. It doesn't actually factor in, and it took a yeah, considerable extra work to refine this technique to get these trade-offs for depths below log k. Okay, so to say a bit about the form of this lifting theorem, it looks something like this. We get that the depth D AC0 formula size of the iterated permutation matrix multiplication problem is at least the minimum over all depth D join trees for the path graph of length k of some complexity measure of the join tree J. Okay, it's a bit complicated to define, but okay, here's essentially the definition. Okay, so the lower bound has the form n to the c, where c is the constant minimum over join trees J. Then we look at the maximum over all graphs that appear in the join tree. So every subgraph of the path that labels a node in this join tree. Now it has some children G1 to GM, and we take a permutation of those children. The children are given in some order. We're allowed to permute them according to a certain restricted type of permutation, which we call a shift permutation. I'll define this a bit later in the talk. Okay, and now we have some score function of that sequence of subgraphs, G sigma 1 to G sigma m. Okay, and I'll illustrate in a moment what the score function is. And now the version of this lifting theorem that we get for SAC0 formulas, so when we have restricted and fan-in, we get a slightly stronger lower bound without this restriction to shift permutation. So if you allow any permutation, then interestingly, we get the bounds for SAC0. When you restrict the shift permutations, it gives AC0. Okay, so here's the definition of score, and I'm going to illustrate this in a sort of visual way. But the definition is we take the sum from j equals 1 to m of the number of connected components of the graph G sigma j that are vertex disjoint from the previous graphs, G sigma 1 to G sigma j minus 1. Okay, so you can forget about everything on this slide for the moment, and I'm just going to try to illustrate now some of the combinatorics that go into proving a lower bound for this score function. So that's the sort of combinatorial game that we want to play now, is to lower bound this score function with respect to the worst permutations. Okay, I'll illustrate this in terms of what I'll call toothpick cover problem. So the setup is this. We're given some sequence of rows of toothpicks. So it's toothpicks arranged in a row, arranged in rows. And in total, these cover an interval of length k. And here's how we define the score of this configuration. So the first row contributes 3 points to the score. And now we can, because there are 3 toothpicks, so now consider the shadow cast by this first row. And anything touched by the shadow, even at just an endpoint, is considered to be killed. Okay, so it's not going to contribute to the score. But we don't remove it. We just don't count it in the score. So now when we take the next row, we get an additional 1 point from the one untouched toothpick. And now we look at the shadow of the first 2 rows, okay, including the toothpick that didn't contribute to the score. This kills any points from the 3rd row, and then, yeah, we don't get any points from the 4th row, 1 extra point from the 5th row, and that's it. So the total score here is 5. Now, can we do better if we're allowed to reorder the rows? And the answer here is we can do better. So here's a rearrangement of the rows, which achieves a score of 6. Okay, so 1 better in this case. Here's another example of a bad sequence of rows, which it obtains a score of 1. But we can easily do better by the following reordering, essentially transposing every other row. And this gives a score of 5. Okay, so a score of essentially k over 2. And so first sort of combinatorial result that comes up in our lower bound is for any covering of an interval of length k by rows of unit length intervals, there's some ordering. There exists some ordering that achieves a score of at least k over 6. And here the constant 6 turns out to be optimal. And the proof analyzes a sort of greedy algorithm that just you repeatedly pick the next row that maximizes the gain in score, essentially. Here's an example of a sequence of rows which is in greedy order. Okay, it satisfies this greedy criterion. And this turns out to be an extremal example, as I'll explain. All right. So this is in total covering a path of length 41. And it achieves a score of 10. So we get 3 points from the first row, then there's 2 points from the next row, and then 1 point for each of the next 5 rows. And note that the maximum number of toothpicks in any row here is 3. So actually the first 7 rows here, you can see have each have 3 toothpicks and everything else has 1. And it turns out that you can generalize this example if you want maximum number of toothpicks to be t in any row, then you can, by a generalization of this, get length roughly 3t squared and score of t squared over 2. And it turns out that for any given t, this is the optimal ratio you can achieve under this greedy ordering. And the proof turns out to be quite neat. It's established by a linear program duality for a certain linear program with Catalan t number of variables that bounds the performance of the greedy algorithm. So that's one sort of neat tidbit from the paper. Now we can generalize this slightly by considering intervals of different lengths that are still covering a path of length k. And we define the score in the same way, just taking into account the number of intervals in each row, not the lengths of intervals. And so, so this has score 7. And okay, very simple corollary of the first theorem is that for any covering of an interval of length k, oh, well, sorry, this is the original theorem that we just saw. Yeah, the generalization is if the rows have intervals of length at most L, then there's some ordering that achieves score at least k over 6L. Okay, so that's straightforward. Let me now just simply restate this theorem in terms of coverings of the path graph, okay, in order to sort of align this with what was on the previous slides. So for any covering of the path of a path of length k by some subgraphs G1 to Gm, where the maximum length of any component in any of these subgraphs is L, there's some permutation sigma of 1 to m, such that the score of this sequence, G sigma 1 to G sigma m, is at least k over 6L, where the score is defined in this way. Okay, the components of sigma G sigma j that are vertex disjoint from the previous ones. This is exactly, the intervals that are not in the shadow of the previous ones. Okay, so now we're interested now in the same question, but we're going to restrict ourselves to a certain type of permutation. We're not going to allow any reordering of the rows, but only reorderings according to a certain class of permutations called shift permutations. Okay, and these are just where every cycle is just a cyclic shift of some consecutive sequence of intervals. Okay, so we have an example here in cyclic notation. We have the cycle 1, 2, 3, and then 4 is fixed, and then the cycle 5, 6, 7, 8, and then a transposition between 9 and 10. This is one example of a shift permutation. Okay, another example, which we actually saw already, that we can improve the score here to like k over 2 by transposing every other row in cyclic notation. Yeah, we can see this fits the definition of a shift permutation. Okay, and we increase the score from 1 to k over 2. And it turns out that this is actually right. So I guess I didn't state it yet, but so you can always achieve omega of square root k over L. That's the theorem. And it turns out that this is the best possible. as this example shows. So here we have like 16 unit length intervals, and we have a score of 4. You can do a little bit better by this shift permutation. Okay, that gives 5, but in general order, yeah, you can achieve omega root k over L, and that's as best possible. All right, so here we've stated both of these results for all permutations, and for shift permutations, we can always obtain score at least k over L or root k over L in the case of shift permutations. Now to relate this to these lifting theorems, so if we simply plug these results into our lifting theorems by selecting the optimal shift permutation or optimal permutation for any given sequence of the children G1 to GM, plug this in for the score, we get these bounds in terms of the maximum component length in any of the graphs G1 to GM. And from this, it's fairly simple to extract these aforementioned size depth trade-offs. So the depth dAC0 formula size of PMMNK you get is at least n to the k to the 1 over 2d. This 2 comes from the square root. And for SAC0 formulas, we get the type bounds of n to the k to the 1 over d. All right. So yeah, so this hopefully gives some idea of what's in the paper. And of course, you can see the paper for details on this. So thank you for your attention.